Maybe I start and then we... Hello. Good afternoon. Welcome to this concluding discussion of the MPC and RL course. Joschka and I are drinking a coffee together with you, if you like. And we want to have a gentleman's discussion about the eternal question if MPC or reinforcement learning would be the more powerful technique. You can all be judges and you can also ask questions if you like. We will not record the questions, so they will be either repeated by us or by the tutors. So for the remote participants, please put your questions into the chat. Yes. Okay, Joschka. Maybe I start and then you can ask me questions. So what is your prime reason why you prefer reinforcement learning over MPC?
Well, the sort of naive and trivial is, I guess, because that's the first thing that I learned. I was exposed to these ideas from reinforcement learning much earlier than I was exposed to ideas from MPC. Yeah, I mean, I have to say I was fascinated when I saw the capabilities of MPC when you can learn a good model. Yeah, so in that sense, I think it is very powerful, given that you can learn a good model in a short amount of time. Then MPC can be quite good. But yeah, so I think I came more from an artificial intelligence background, and there I think it was inspired a lot of by human learning and by psychology and ideas from Skinner and these things, and that's, I guess, more how I found into this niche. Yeah, so it was only very much later that I got to know MPC as a technique itself, I would say. Yeah. And maybe I can give you back the question, actually. So, yeah, how about you? I mean, when did you start learning about RL, and what's your take on maybe important differences?
Yeah, thank you. Maybe I should answer why I would prefer RL, maybe, to make it a bit more gentlemanlike. No, actually, I obviously learned about MPC earlier than RL, but when I learned about RL, and what really fascinates me about RL is its capability to solve problems with arbitrary state spaces, maybe without even knowing what the state space is, with discrete states, continuous states, non-continuous functions, non-differentiable functions, stochastic systems. So this is really extremely powerful. While the world where I come from, MPC, I'm so to say already, let's say, one of the more general people in MPC, because we do nonlinear optimization, right? I mean, the large part of applications in model predictive control is based on linear models and on linear programming or quadratic programming. That's basically what MPC in practice is nowadays, right? But nonlinear models seems like, oh, we are already so general. That's what I felt until I heard about RL, and then all these other things that are not linear, non-convex, non-continuous, even changing state dimensions. So that's what fascinates me about RL. So somehow this ability to detect and find state spaces, which obviously is very closely connected to deep learning. And this, I mean, the part we didn't talk so much in this school, but you talked a bit about the representation capabilities of deep neural networks are, of course, a game changer for lots of things, and also probably for the field of optimal control. And that's why I think that we have to learn about reinforcement learning, and that's why I was so happy to do the school with you, because I learned already a lot. So thank you, actually. Yeah, on the other hand, I would also like to say that you remember when we started, we had this discussion about Bellman and Danzig, right? And I found this interesting citation from one of the collaborators of Bellman, who said that for a long time after dynamic programming was invented, so to say, they felt like in practice LP was doing the job. Yeah, so many practitioners did use LP. So I want to somehow still and I still think this is true today. So somehow the ability to solve and not to search of all these, let's say, optimization approaches is powerful. And maybe one other take I took from the course is that some RL approaches are, so to say, not really RL in the strict sense that they are doing Q-learning and or policy, policy or value iteration, but that they actually also start at the given initial point, like Monte Carlo tree search is also leveraging on the fact that you only want to know the optimal plan from the current state and not for every possible plan. So you don't optimize actually the policy, but you optimize the path. And so in that sense, this fact that MPC optimizes a path and RL optimizes a policy, so to say, is also getting blurred. And I think maybe I put a few words so that we take away our points. Yeah, maybe I just put the keywords here. So we have this LP, this old divide, LP versus DP, yeah? Which comes back to, to Danzig, of course. Okay, now we are really preposterous, right? But we have these eternal, fight, so to say. And I think that what we, so to say, do in MPC is we optimize a trajectory, right? That's also what LP approaches do. They work on a trajectory optimization in some form, yeah, where here it's actually the policy optimization, which I would find, I mean, it's one of your approaches, but I mean, it's directly looking at the full policy, so to say, and maybe, yeah, you work in state space in some form. Yeah. So here we work, yeah. Obviously, we have states on both sides, but here we have the state space, and we tabulate and represent functions in state space. Yeah, I wanted to still say here we solve, right? And here we search somehow. But at the end, things get sometimes similar, but I just want to put things on one side. You remember we follow Larry Biegler's search or solve methodology, and I would say somehow I feel that we are a bit more on the solve side with MPC and with RL a bit more on the search side, but this is something that you can contradict. I give you the microphone.
I don't necessarily want to contradict. I just wanted to say I liked your addition, though, because you said that dynamic programming for you was searching intelligently, and I share that view. So I think the structure of these Bellman equations and this bootstrapping ideas, they structure the search, yeah. So and they make it possible to reuse these intermediate results and focus the search. So so if I may, I would put intelligently.
You're right. I completely agree.
Yeah. So let me maybe pick up briefly on the point that you mentioned. Right. I mean, so these big function approximators, neural networks, deep neural networks, have been a game changer. That's true in RL, and it might be that it's also finding more and more its way into MPC ideas. And but then my question would be to you, maybe. I mean, I think one of the advantages that I can see that are in the MPC field is that you can give theoretical guarantees, stability guarantees. You can deal with constraints in a natural way. That's something that it's somehow much harder in reinforcement learning. But once we introduce these very nonlinear high-dimensional function approximators, do you see a way forward maybe also to really save some of these theoretical results over in that case maybe?
Mm-hmm. Hey, that's an interesting question. So maybe I first note this point, right? Actually, so you said here constraints and stability guarantee. And stability. Yeah. Right? These are, let's say, pros.
Yeah, maybe we should switch the names up there.
No. But I think that's a gentleman's discussion, right? We can be, because I also said what I really think is here the, is it like discontinuous systems, right? Yeah. Continuous stochastic. I mean, that's where you're really having difficulties in MPC. You have, combinatorial. I mean, you can do combinatoric sometimes in MPC, but it's more powerful probably here. Combinatorial optimization. What else can you do here? It's like unknown dimensions, right? Yeah, unknown state dimensions.
Right, learning state features, right?
That's
a very powerful thing with these deep neural networks.
Yeah. I find Q-learning particularly exciting, so to say, in the sense that you could do directly model-free. Okay, so that was... okay, but now your question. Your question was, how could we maybe bring some of these constraints and stability to to the RL world, and or the DP world, maybe more general. I would say that it's... I would somehow try to base everything on, let's say, cost-to-go representations, which the first thing is maybe, I don't know why, but maybe directly introduce infinity as a cost. I don't know whether that's existing maybe or not, but so to say, work with an extended value extension to be able to deal with constraints, maybe. Yeah? But once you have stochastic systems, you have to define what you mean by constraint satisfaction, because if you have a certain probability of violating them, then we would need to to give already infinite cost to a violation, then you are, so to say, making some trajectories impossible from the beginning, which maybe might be too conservative. So if you have constraints with stochastic systems, you need to first define somehow what you want. But after you did, one could have maybe, so one idea could be extended reals in this world. So to basically represent not only a cost function, but also a feasible set with a neural network, maybe. The Q function could not be just a function, but it's also representing maybe the set. That would be my point to maybe it helps, maybe not, for constraints.
And approximations of the regions where you might end up in with...
Yes, so to or one could actually, that's another interesting idea, right? So that we both, that we try to, a bit like level set methods, try to represent sets by functions which are, so to say, by basically inequality constraints, so to say, right? So we could learn the Q function together with the Q feasibility function, which is negative if it's feasible, so to say, right? So that would be another way to somehow express, I don't know, maybe that could be, both could be either infinite values or another object that you use for that would be something exciting. And about stability, it's just brainstorming, right? But one thing that when we did this course, I realized, okay, all this beautiful monotonicity in dynamic programming is there and helps us. Basically, every stability proof in MPC is somehow based on monotonicity of dynamic programming. And so maybe one could try to do during learning to impose, so to say, on the Q function an inequality that directly enforces, so to say, the stability proof that we would get otherwise. Also just brainstorming, I didn't write anything down, but it could be that we try to somehow restrict the function approximators.
The update for the function.
Yeah, we somehow impose constraints on them, on the function approximators, maybe.
I don't know.
Yes, either, I don't know. Or we parameterize them so that they can only parameterize functions with certain properties. Like you might even be able to, I don't know, to devise neural networks which only can represent convex functions. I don't know, right?
There's input convex neural networks.
Okay, input convex neural networks. That sounds interesting. I did not hear yet. Yeah, but okay, that's enough brainstorming from my side. Maybe some remarks from the audience or questions that you want us to discuss. Yes, Nick, please.
If you were in front of your master's or, let's say, PhD, would you choose the same field or would you...
So the question is, if I would do a master or PhD again, right? Like 20 years ago, I did my PhD, and now if I would choose again, would I do MPC, which I did? I did a PhD in MPC, or would I do an MPC? It's too difficult to say. Actually, my 6-year-old son is already quite philosophical, so he would have answered, if I I mean, he's always happy, and I'm the same, so to say. So he said, I like this more what I did, right? So I would probably choose again MPC, but on the other hand, I don't know how it would have been, how it would have felt if I would have chosen RL, and maybe I would be as happy if I would have done RL. Probably I would, but so I don't regret that I did my PhD in MPC. So I'm really, but I also don't regret that we did this class and that we learned from each other. So I look forward to actually getting these fields together. And also next week we will have exciting talks, right, by two experts who already work at these intersections very successfully. So I'm really still looking forward to what happens, and also to your projects, by the way. But I'm happy to be an MPC person from training, let's say.
Thanks. Yeah, I think that's a very good answer. And I have to say, I'm glad that I don't have to choose. I think it's great that we can look into both things and like today, think about how to combine them and how ideas from one field can be fruitful for the other. I think this is very exciting to me right now. I don't know. I mean, I come from computer science, and I guess the path led me naturally more towards these ideas that came more out of this computer science community, which was our RL. But yeah, I absolutely see a lot of potential to learn from MPC, and therefore I think it's great to work at the intersection and see how we can make progress incorporating these ideas with each other.
Maybe I want to add a bit, because your question obviously has a component of what should a young person do today, right? And so I still think that good education in optimization, convex optimization, differential optimization, but also maybe combinatorial optimization would be extremely useful for anyone working in either of the two fields. So in that sense, this is something that is never wrong, I think, and I would very strongly advise, because it's also at the basis of neural network training and so on, right? And this is actually the other thing that maybe what I didn't study as much as I would have liked in my studies, I think, and which obviously I think you should study now, is a function approximation, so to say. I mean, not only deep neural networks, but all kinds of function approximation, because that's basically at the basis of everything. Like optimization and function approximations are so important ingredients for nearly all applications of, let's say, applied math and engineering and computer science. So I think it's good to know about these two things. I don't know if one of the two is more on one side. No, they are both really, that's a similarity. I think they are both based on function approximation. I mean, MPC is also based on identified models a lot, and RL is based on optimization a lot. So they are sharing optimization and function approximation. Yeah.
So there's a question from the chat. Which are the ideas from the other field you see now to apply in your own field?
Okay, so the question from the chat is, which are the ideas from the other field that you want to now apply in your own field? Yeah. Okay, so I start maybe. So one of the ideas I definitely want to apply in my own field is, let's say, it's identified models, so learn models from black box models, basically, right? And nonlinear black box models. This is, I think, a direction I like to explore. We discussed some other issues, but quite technical also. But one other thing that I would also find interesting to explore is, I assume in my world, right? If you have a model, and let's say I prefer the the model-based RL also, because it's more data efficient. And in my world, I would focus on data efficient. When I have a real system and I'm interested in physical systems that you control that are really with experiments, you don't want to repeat that a million times. You cannot. You cannot parallelize. Mostly, you can buy 10 KUKA robots, but you can't buy 10,000 KUKA robots, probably, I don't know. So I would rather focus on things that are data efficient, and that's, I think, is model-based RL or model-based approach. So once I have a model, I would also say the cost function and the constraints I take them for granted. I think that's what the user has to specify, and we have to tell what we want, so to say. So for me, the learning of the model is one ingredient that I want to take over from your world, Joschka. Learning the model. And the other, and that's maybe a bit where really reinforcement learning comes into play is learning terminal cost functions, right? Because when we have MPC in practice, we obviously, even if we do a deterministic system, we, let's say you have some forecast data for solar irradiation over the next day or such things. You never know what's the terminal cost, right? And you would want to do, and you know that it should be a terminal cost that reflects the stochastic nature of things to come afterwards. Yeah? Even if for one day we think it's mostly deterministic, we definitely don't know how the weather will be in 2 weeks. Yeah? And so what is like our cost function for a battery storage or for a heat storage system after 1 or 2 days of prediction? And I think that here learning maybe, cost-to-go functions like terminal costs would be the two things I want to learn. Models and terminal costs. I don't care about constraints. I want to impose constraints myself. And my objective I'm also happy to specify myself. But I want to learn a model and a terminal cost, so to say. Mm-hmm.
So I mean, something that I'm excited about is trying to leverage some of the ideas in MPC, in optimization of these, for instance, these multiple shooting methods. We talked about that also today briefly. I'm not aware. I mean, of course, I don't know everything. There might already be something out there, but I'm not aware that this is used anywhere in the RL world. And especially thinking about how this could be applied in the model-free case, which is, somewhat counterintuitive maybe and a weird idea, but I think that it could be interesting. And as well, the way to impose constraints. This has started in reinforcement learning as well, but I think it's much less mature than it is in MPC. And of course, there's this whole issue of stochasticity that you mentioned, which probably does give additional headaches, of course. But I still think this is exciting. It would open a lot more doors for industrial applications if we, first of all, can be data efficient, of course, and that's something where models are very good to be used, and then at the same time also be able to impose hard constraints and provide guarantees. Yeah, so that's for me, I think, what's very exciting to try and incorporate more into RL ideas.
Okay. There's one more question.
For the application part, which one MPC or RL is more useful and efficient for autonomous driving systems, self-driving cars?
Okay, so the question is MPC or RL more efficient for autonomously driving cars? Autonomously operating systems. Maybe I should start by saying some observation. Yeah? If you think of an autonomous car, for me, the main task or the main difficulty in autonomous driving is, so to say, to understand in which situation the car is. Yeah, like, for example, image processing, which is part of it, right? I mean, we have sound and eyes. That's from this we construct the model. If you know where this car is, where people are on the street in front of you, I mean, the model that predicts that a person might move a bit to the left or to the right, that's relatively trivial and small dimension compared to this estimation task. So I think my personal opinion of autonomous driving, it's not a control, I mean, it is a control problem overall, right? But if from the control perspective, I think the planning problem is much less challenging than the observation problem, the estimation problem. So in that sense, I think there is definitely a really big space, so to say, for anything that has to do with getting truth out of sensors, so to say. Once I would have a little model, let's say 10 or maybe even 50 states of my car and of my maybe possibly 20 obstacles with whom I could collide, I would say this is probably easy to solve with maybe with MPC and optimization-based approaches, but probably also with any other approach, so to say, because it's relatively simple compared to the rest. Yeah. this is maybe a bit pessimistic for my own business, right? Because our business is to solve optimization problems. But somehow I think if you have the computer on the car working, I guess 99% is, so to say, dedicated to understanding what's happening in the world, and I mean, have clouds in front of you and maybe mist, and it's dark and you don't see the street and so on, and you need to. Yeah, I mean, there is, I think, not much space for exploration, by the way, so I always thought of it, but somehow I don't think that you will have a controller that starts to play with your car in order to identify it. I mean, a little bit maybe, but maybe also not. So I think I as a driver, when I start to do these experiments, like, let's test how our brake works today, my family already complains. And I mean, somehow you rather drive a bit more conservatively and you don't get to the limits, so to say. I mean, as a race driver, maybe differently, but on a daily basis, I think there is probably not so much on this exploration stage in a car. Okay, so that's my personal views on these. So at the end, I think, my answer would be it doesn't so much matter because the control problem itself would be so easy, so to say. But I mean, to find a good path could be still a nice MPC problem, let's say. So, and we look at solving that, and I find that interesting, right? And yeah, okay, good. Yeah, that was my part of the answer.
Yeah, thank you. I partly agree. I think, yeah, sure. The estimation problem is a hard one with real-world data in all kinds of situations to really try to reliably estimate where you are, where all the surrounding objects are, and so forth. Yeah, and then the control problem, I think, gets difficult. I mean, is made difficult by having many other humans around you that are not that easy to predict all the time, right? And that don't always act rationally as well. And I think that's why it makes sense to incorporate some data-driven optimization, be it RL, for instance, for some of the tasks where you just want to learn from the data. How are people behaving, in expectation or something like that, and you can use that in your optimization directly. Because I mean it's dynamic situations that keep evolving in sometimes very unexpected situations, and you need to be able to deal with that. On the other hand, I don't think. I mean, I personally don't think that learning the whole autonomous driving problem end to end is the way to go. Yeah, I think there's. I think there are many things that don't need to be learned that can be addressed more with other techniques. But on the other hand, also, if we think about long horizon optimization and the fact that for many human behaviors, it's very hard to come up with good models. Then I think this has definitely its place with RL, but also I definitely see a place for MPC in the whole scheme also.
So maybe I want to add, because you mentioned these, you want to learn human models and how humans would behave in expectation. I think this would be, I want to contradict. No, and I think I think you don't want to model humans in expectation, because I mean, if a human stands next to you at the road, then this human in expectation probably doesn't jump on the road, but he or she can jump on the road, right? And so if I'm on a motorway, and I drive there very fast, and there is a person standing maybe even 2 meters away from the road, I slow down already, even though I know in expectation this person will not jump 2 meters or 4 meters even to my road where I'm running with 100 kilometers. But you slow down. And I think this is because I do, so to say, a worst case approach, right? And so I think that we should, and this is maybe why I say maybe there could be, now I'm getting more optimistic on MPC, obviously. No, because you could incorporate the constraints and the robustness, like the worst case behavior, like a min-max optimization, which could be either solved with RL or DP-like approaches, but you want some form of guarantees. So I would rather go maybe for deep MPC, robust MPC in these planning problems, and you, so to say, adapt to the uncertainty by, for example, driving slower. By the way, I just realized that yesterday I had a funny situation, not with you, but do you want another coffee?
Sure.
Yeah. I do a little experiment. I just want to illustrate one thing of a robust optimal control, right? So you want some coffee, I guess, right? Good. And now I do something a bit unexpected. Do you want some milk?
No, thank you.
Okay, good. Okay, so maybe now I will put my own coffee. And I put a bit of milk into it. So my question is actually, what did I do differently? When I don't know how much milk my person wants, then I move slower.
Okay,
I already try, right? And I mean, so I hope that you would want milk, then I would just pour it, and while I pour it, I ask, how much milk do you want, right? Okay. But for me, myself, I could just, I know what I do, what I want, so I do it quickly. Right. And that's a bit like this, it was some form of robust MPC for moving slowly.
Yes. You don't know.
I want it to be feasible, right?
Yeah, exactly.
Yeah. And so in that sense, that's, I think, a part of business also for autonomous driving.
Yeah. But I agree. Saying that, learning the behavior and expectation probably wasn't the most accurate thing. Yeah, exactly. So, exactly. So it's probably a better idea actually to prepare for the worst case and take that into account. But still, maybe on this note also, how about this long horizon optimization, right? I mean, in the city, maybe, for instance, if you drive in the city, then horizons can be rather short, maybe in an intersection or something, and then the situations become complicated because there are many different participants, like pedestrians and bicycles and so on. But the horizons you plan for are maybe shorter, but on the highway, for instance, they might be very long. You want to take into account the road situations many kilometers down, maybe even, or at least several hundred meters and so on. And so how, for instance, how would MPC deal with this situation of these different horizons, maybe even?
That's a good question. Let me maybe first say that I think the prediction horizon of a car, let's say about the dynamic driving behavior, is probably still in the range of a few tenths of seconds, maybe. Yeah? I don't think, the rest is like the route finding problem of where you want to go. Do I go from here to Berlin via Offenburg or via Basel? Yeah? So that's what our navigation system solve for us. By the way, with a technique which is it's mostly it's actually a mix of probably online and intelligent search, right? It's Dijkstra which is at the bottom of it, right? So there's okay, but anyway, so what I wanted to say is the end. If you're so to say settled on which road you want to drive, let's say, if this is settled. I think you can predict 1 or maybe 10 seconds and 20 seconds maximum, and then you would be fine.
But if there's cars in front of you that brake, for instance, and that would, affect the cars that are immediately in front of you, so you should take that into account, shouldn't you?
Okay, so so if there are cars in front of you, Actually, I remember there might be a longer-term memory question. So like there was this crazy car overtaking you, and you felt like, oh, this is a dangerous driver, I better keep a distance, and then you meet this person, like you see, it's the same car, 2 cars in front of you or something, and then you maybe don't overtake because you think this is probably an unpredictable driver or something. So okay, maybe there are some situations where you rather choose to predict more.
I think there are intermediate range horizons that you might want to incorporate. But this is I don't know, maybe on the more general side, like how would you incorporate
Actually, one interesting question is how I would do a safe planning MPC in this context. And I'm not sure, this is crazy brainstorming, right? But I would assume that you, for a finite prediction horizon, I always want to have a safe terminal state, so to say, right? Safe in the sense that you know you can stay there infinitely long. And that's probably on the motorway difficult to get, maybe on the side, but actually which isn't so unrealistic. So if I would do, so to say, driving at least in a neighborhood with kids and so on, I would probably just always plan that I drive for the next 10 seconds and then stop. I plan that I stop. Always, and that would make me, so to say, completely safe, fail-safe, right? As long as my model, and with some robustness margins, of course. So then I would be able to not come into the situation that behind that car runs where I don't know yet, or behind that corner is. Yeah. Of course, it would make me drive a bit slower. An alternative could be also that you plan a trajectory where, so to say, at every point on your prediction horizon, you also have a plan B to stop. That might be slightly it's somehow like a safety constraint. That, so to say, but it's making a tree-structured optimal control problem. So at every time step, you get like the nominal plan and then a plan B, which is, so to say, what if something happens and you want to stop immediately? So that could be, so these two approaches might be ways to get somehow inherent safety. And robustness, of course. So that would be my ideas about that. But maybe you have more, or we have more questions. Yeah.
So this is also regarding robust MPC. Is there any relationship between robust MPC and reinforcement learning?
So, is there any relationship between robust MPC and reinforcement learning? Okay, I think maybe first my point. You can add. I think the robust MPC. So I presented robust dynamic programming in one lecture here. We didn't really focus on robust MPC numerics from the pure MPC perspective, but basically the robust dynamic program problem I think we can well define, right? It's a min-max play. It's like a two-player game actually. And in RL, you always use the stochastic formulation of, so to say, of a system. But if you know that the system, the counter system is an adverse player, so to say, in practice in AlphaGo or wherever, people use this fact that this is not just a stochastic system, but it's a player that is maximizing the contrary. And of course, the let's say from my optimization perspective, this min-max structure of robust optimization can be sometimes exploited in the algorithms. And obviously, for the training, you exploit it by just playing against a twin, so to say, right? So that is, yeah. So in that sense, I think robust MPC and RL are definitely very related because, and maybe I should say that the robust MPC problem is inherently much more difficult to solve than the deterministic MPC problem. Really, it's not just solving, but somehow it's also searching about all possibilities. Yeah. And I think RL is, or any DP approach is suffering less from the addition, the transition from deterministic to robust. This transition is easier, I think, once you're already anyway in state space, so to say.
Exactly, yeah. I'm thinking if I have to add anything. No, I think I actually also have an extension of that question maybe that I would like to ask, and that's you just briefly mentioned sometimes explicit MPC. I was wondering, can you say a little bit more about the relationship between that and the RL ideas maybe? Because it sounded sometimes like it would share some of this amortization of this optimization process like we do it in RL maybe.
Okay, thank you for the question. So we didn't touch much on explicit MPC, but basically, I mean, at the end, the product of explicit MPC is basically the same as policy optimization, right? You have a parameterized policy and you can evaluate it. And how you represent it is probably debatable. And in the classical explicit MPC world, you would take a QP, a parametric QP, solve it explicitly, and get piecewise linear functions on polyhedral regions. But nowadays, people also look at approximating it with other architectures, and in particular, for example, ReLU functions have the same smoothness property as the MPC law, so some people train it on. But what you do then is you just call your MPC solver, so basically like numerical software that people like I do develop, right? They take it, maybe they solve it, call it on 1,000 computers at the same time, right? You can just, and then you sample somehow in state space and you approximate that function. You don't do anything that's related to dynamic programming. I mean, then that would be my way to distinguish. I mean, you could also say, and then but in my definition, explicit MPC is, so to say, taking the problem that's usually solved online in MPC, I mean the trajectory optimization problem, and solve that offline and many times and try to, so to say, memorize at what situation it would recommend what. So it's like training your policy representation on data generated by MPC, so to say.
I mean, so that sounds very, very... Yeah. That sounds very, very related to these guided policy search ideas by Sergey, for instance, using MPC to generate the training data and then basically training that into a policy representation represented by a neural network.
Okay, so then we will see and we will ask him if he would call his things explicit MPC or not.
Yeah, exactly.
Anyway, okay.
But it sounds like also a very close connection to these RL ideas, not based on dynamic programming then, but at least with this heavy training phase and then cheap evaluation later on. Yeah, that's interesting.
Let me somehow say why I feel like, I mean, in some applications there might be benefit, of course, to parameterize policies. What I really maybe should say, what I like about all this fact of online optimization is that you could relatively quickly change situations, so to say, completely. I mean, you can just say, don't follow this trajectory, but that one now. Or, you don't have to train for all possibilities, right? So the data space of your optimization problem is not just, I mean, obviously we can call it state space, but I mean, it could be that a user specifies constraints a bit differently. And so you can very quickly adapt to change desires also, if you have a good learned model, and then you do just online optimization with it.
Just think about think about the example I introduced at the very end with this wall that was shifted. I mean, this would be discrete state in action space, but just there was a change in the structure of the environment, and then all of a sudden, quickly there was a better solution available, and then you would be able to find that very quickly with online optimization. Whereas with if you have the model available, right? Sure. I mean, thinking of something related maybe in the continuous state in action spaces. But for RL, this takes a while, as we saw. You have to explore and you have to backpropagate the changes, and that takes a while, even with a model. Yeah.
Oh, there's still a question. Maybe we take it as the last one?
Yeah, there are 3 more questions.
3 more, okay. Can you summarize them in 1 or 2? Okay.
Give shorter answers than
yeah, we give shorter answers. Okay, that's a good idea. You're absolutely right. Yeah.
Okay. So the first question is whether the debate of MPC and RL is also a debate of the evolution of computational power. So we have RL with these big super clusters from the Google side, and then MPC on these small embedded systems. This is a picture that would be.
So the question was about, is the difference between MPC and RL also about the difference between limited resources for MPC, like little embedded systems, and large computing clusters for RL? I wouldn't say that it's this distinction, but it's, MPC started as something 40 years ago, like the biggest available computers at that time, working in some chemical plants. I mean, not the biggest, but really probably expensive workstations standing there and doing online computations. But maybe you can comment. Obviously, nowadays.
Yeah, I mean, Sure. I mean, if we want to be completely model free and we want to extract features automatically from the data, then we just need a lot of computational power for this training process, and then evaluation of the policies is rather cheap, right? So in that sense, yeah, we really profit from big data sets and from GPU computation, parallel computation, and so forth. I mean, I was asking myself when this question was asked also, I mean, could this big computational power be exploited in MPC as well to tackle some of these problems as well? But I mean, you still have this problem of state. For instance, could you do something like control directly on pixels in that case somehow? Yeah. But I mean, that would mean you also have to first extract these features automatically because I think directly on the pixels. Learn. I mean, defining a model how your pixels change in high-dimensional pixel space is probably very difficult. But I don't know how. I mean, I think there are some approaches that make MPC itself, the optimization of a QP, for instance, differentiable, and then you're able to back-propagate gradients from solving the QP back through a convolutional neural network, for instance. And that can be probably quite an interesting combination of the two, yeah, where you could actually profit from both, right? You could profit from extracting these nice features. You would have to put them into a model somehow, and then you could use the model to do MPC, and if you could optimize everything jointly, that could be very, very cool, I think. And then you would probably be able to leverage all this computation to extract the features and then do MPC on top. But I don't know. What do you think about that? Yeah.
Exactly. Next question. Maybe I give the micro to you. So.
Okay. So the next question is, can you comment on learning models with RL and learning cost functions with classical inverse optimal control approaches as weights estimation?
Sorry, I need to concentrate.
I also didn't quite. So I mean, inverse optimal control to learn the weights of cost functions.
Yeah. So learning cost function with classical inverse optimal control.
Versus
Learning models with reinforcement learning.
Well, in my view, these are a little bit different. I mean, sure, rewards. The reward function can be seen as part of the model, but in RL, right, we often assume that we also don't have access to the reward function. And if we don't have access to the reward function, for instance, there's, in addition to inverse optimal control, that would be model-based again, you would, you also have the setting of inverse reinforcement learning. And in that setting, you don't actually get any rewards. You don't have observations of rewards. So you basically only see state and action trajectory. So all you're able to see is the behavior itself. And from that, you try to extract a possible reward function that would explain the behavior that you saw. So for me, that would be more closer to the setting of inverse optimal control without having to have a model. And that's what I presented in the very first lecture, where unfortunately the video didn't work as well as I wanted to. But the work that I intended to show there addresses exactly that problem. So this is an approach that we presented called deep inverse Q learning that does something like that.
Yeah, I think it's a very high-level question, but I still want to add a few things. I mean, inverse optimal control is obviously a fascinating idea. You observe behavior and assume that the agent optimizes something. And from the MPC, or let's say from the solve perspective, right, of solving optimization problem, it's just increasing the level of difficulty, because it's basically leading to optimal control problems with some, so to say, equilibrium constraints, as we say. Basically, we say that the controller itself should be the optimization result for some objective function. So it could become very intricate and also very interesting. I should say that obviously the solutions of these problems are severely ill-posed. So ill-defined, because obviously the absolute level of the cost function, the total scaling of the cost function, also any monotonous scaling of the cost function could be completely equivalent, but also very different cost functions could lead to the same behavior. And I want to add one interesting thing, which might be interesting here in this community, because it's not so known. So you know this universal representation theorem for neural networks, for example, right? So whatever continuous function you want to represent, you can represent it with a neural network. And you can prove relatively easily a similar universal representation theorem for convex optimization. And it's really as strong as the following. For any continuous map that you give me from one real Rn to Rm, right, from two vector spaces, I can give you a convex function in both, in the input and the output space, that is basically having as its minimizers exactly those. For fixed one parameter, it would give the other as the minimizer. So it's really basically, for example, a parametric QP in this sense, how we formulated them. So in principle, every continuous function could be represented by convex parametric programs, and that maybe could be an interesting relation to, so to say, Joschka's idea, which is basically these, how did we call them, optimization layers by Zico Kolter and Stephen Boyd. They preaching this, and I think it's an interesting idea that should be explored a bit further. So to say, just apply the brutal training techniques from neural network training, where you just differentiate non-differentiable functions and you do gradient descent. That you apply these techniques in order to basically tune parts of your MPC. So in that sense, but this is not anymore related to inverse optimal control. Sorry for that, but it was this inverse optimality thing. Yeah, thank you. Next question, please.
So the last question for today is: would the exploration ideas of RL be interesting for overcoming local minima issues in MPC?
Okay, the question. Yeah, I don't need to repeat it, right? So would exploitation be an issue to overcome local minima in MPC? I would spontaneously say no. Because, the local minima issue is all about global optimization if I have a perfect model, and exploration is mostly about learning more about the model. If you think of black box optimization, which is so to say, on the search side of optimization, right? In search, you have things like Bayesian optimization. You have also genetic algorithms, simulated annealing. Random search I like that a lot also, just trying out. So you can search a lot of and intelligent search probably has some form of exploitation like Bayesian optimization. So you search more where you think you don't know so much. But I wouldn't call this a problem of global, or versus local optimization. So one could, so to say, use Bayesian optimization to solve the MPC optimization problems, hopefully to local global optimality. That's maybe the relation. But I wouldn't say. For me, in reinforcement learning, the exploration is really about learning the model where you don't know it yet. And that's my control view on exploration.
Yeah. Yeah, I think I agree. Either for learning good models or for learning good Q functions, it's of course also important, this exploration, if you don't want to have a model. Also for learning a good policy in the end. Exploration, if you don't have a model, you need to make sure that you explore, otherwise you can't hope for generalization in parts of the space where you've never been. But yeah, how that relates to local optima in MPC, I'm not exactly sure.
Yeah, but maybe to say, probably the randomness and random search ideas are useful to avoid local minimizers. And yeah, so it could be a technique to basically get rid of some of the issues of local minimization. But I think in practice, once you have a differentiable and nice continuous optimization problem, you should use derivatives, and maybe you restart that randomly a few times. But you should use, so to say, somehow the power of solving, of going. Yeah. And that's what I would always advocate. And usually when you start an optimization solver, a good solver 10 times, and your problem is like a decently formulated MPC problem, it rarely happens that you end up in different local minima. It's my personal experience just. But obviously there are some points where this is absolutely untrue. And that's where I also get fascinated when I said strongly non-convex problems. That's where I think that RL could be an interesting approach. If there's no more questions, then I have something to offer. Maybe after a short break, but I just wanted to offer, if everyone agrees, and Joschka, you can contradict, you can also contradict, but I wanted to come back at the end, maybe after a 5-minute break, about the relation between LP and DP. Yeah, because at some point there was this question when we discussed about the linearity of the Bellman equation in your talk. Some person said maybe there's an LP formulation of dynamic programming, and in the meantime I looked it up, and it is, and I want to present it to you because it's only 5 minutes and it's giving an interesting relation between these two worlds, which is like a bit mind-boggling, but it's interesting, and I think it's good. It's not too complicated. But let me, do you agree? We do that in 5 minutes and as a Blackboard lecture? Okay, good. Okay, then, but first let's thank all of you for the nice questions. Thanks, Joschka, for the gentleman-like discussion. We didn't fight each other. That's good. We didn't beat. That's great. Better than my son and his friends. Okay, good. Thank you very much.